Kepler 186f, one of my favorite planets, slightly larger than Earth, orbiting its star in a region where temperatures might allow liquid water to exist. A world we've never seen, never touched, yet one that quietly changed how we think about planets beyond our own. When astronomers announced its discovery, it wasn't dramatic or loud. It was a simple realization. Planets like this aren't just ideas anymore. They're real places. And they exist in numbers far greater than we once expected. Kepler 186f was found by a small space telescope with a very patient job. And somewhere above us tonight, trailing behind Earth in its orbit around the Sun, that silent telescope drifts through space with its work complete. We call it Kepler, and during its years of patient watching, it discovered more planets beyond our solar system than humanity had found in all previous history combined. Rocky worlds, gas giants, scorching hot planets, frozen ones, and many that fall somewhere in between. NASA eventually announced Kepler's retirement, marking the end of a mission that forever changed how we see planets beyond our own. You're listening to The Drowsy Astronaut, where tonight we explore the remarkable legacy of the Kepler Space Telescope together, diving deep into the planets it discovered and how those discoveries changed what we know about exoplanets. By the end, you'll have a much clearer picture of how common worlds like these really are. The video is tuned to 432 Hz and is designed for slow listening. Something to accompany you as you rest, drift off, or simply unwind after a long day. What time is it for you right now? Which part of the Earth are you settling in from? If you'd like to leave a small piece of yourself in this gentle exploration, the comments are always open. And if these calm journeys help you relax, a like or subscribe genuinely helps this channel continue. Now let us begin with the mission that changed everything we thought we knew about planets. Before Kepler launched in March of 2009, humanity knew of fewer than 400 planets orbiting stars beyond our Sun. Most of these had been discovered through a technique that detected the wobble that planets induce in the motion of their host stars. The planets we knew about were mostly giants, massive worlds like Jupiter or larger, because smaller planets produced wobbles too subtle for the instruments of that era to detect. The question of whether Earth-sized planets were common or rare throughout the galaxy remained genuinely uncertain. Kepler was designed to answer that question by watching for a different sign of planetary presence: the tiny dimming that occurs when a planet passes in front of its star as seen from our perspective. This dimming, called a transit, blocks a small fraction of the starlight and reveals that something is orbiting, even if that something is too small and too distant to see directly. The technique had detected a handful of planets before Kepler, but no one had applied it systematically to thousands of stars for years at a time. The mission that emerged from the drawing boards was elegantly focused on a single purpose: detecting the transits of planets as small as Earth around stars as bright as the Sun. Every aspect of the telescope's design served this goal, from the size of its mirror to the sensitivity of its detectors to the stability of its pointing. The spacecraft was built to measure brightness with precision better than 20 parts per million, sensitive enough to detect an Earth-sized world, crossing a sun-like star. The field of view that Kepler would monitor contained approximately 150,000 stars, a sample large enough to yield statistically meaningful results about how common different types of planets might be. If Earth-sized planets in habitable orbits were common, Kepler should find dozens of them. If such planets were rare, the absence would be equally informative. Either answer would transform our understanding of the galaxy. The launch occurred on March 7, 2009, from Cape Canaveral in Florida, with the telescope riding a Delta II rocket into space. The spacecraft separated from its upper stage and began its journey not into orbit around Earth, but into orbit around the Sun, trailing behind our planet in a path that would slowly carry it farther from us over the years. This orbit provided the stability needed for precision measurements, free from the disturbances that Earth's gravity and atmosphere would have introduced. Commissioning the telescope took several weeks, as engineers verified that all systems were functioning correctly and calibrated the instruments for the observations ahead. The first images from the telescope showed the star field that would become Kepler's home for the next 4 years, a region spanning parts of the constellations Cygnus and Lyra. Within this field, stars of every size and color waited to have their light measured with unprecedented precision. Science operations began in May of 2009, with the telescope settling into the routine of continuous observation that would characterize its mission. Every 30 minutes, Kepler recorded the brightness of its target stars, building up a data set that would eventually reveal the tiny dips in light produced by transiting planets. The data flowed back to Earth regularly, transmitted via the deep space network that NASA operates around the globe. The first months of data contained the information needed to detect the easiest targets: large planets orbiting close to their stars, which produce the deepest and most frequent transits. These hot Jupiters, as astronomers call them, announce themselves quickly, their transits occurring every few days and blocking enough starlight to be unmistakable. But smaller planets, in longer orbits, would require patience. Their transits rarer and shallower, detectable only after months or years of accumulated data. The early results exceeded expectations, with the first confirmed planets announced within months of the mission's start. Kepler 4b, a Neptune-sized world orbiting close to its star, was among the first batch, followed quickly by several hot Jupiters that had been detected through preliminary analysis. Each confirmation required careful work to ensure that the dimming was truly caused by a planet rather than some other phenomenon that could mimic a transit signal. False positives posed a significant challenge that the Kepler team worked continuously to address throughout the mission. A background star with an eclipsing companion could produce dimming similar to a planetary transit, as could star spots crossing the stellar disk or instrumental effects in the telescope itself. Each candidate planet required investigation to rule out these alternative explanations before it could be promoted to confirmed status. The sheer number of candidates emerging from the data quickly outpaced the capacity for individual follow-up observations with ground-based telescopes. The team developed statistical techniques to assess the likelihood that candidates were genuine planets rather than false positives, eventually allowing mass confirmation of hundreds of planets at once. This approach accelerated the pace of discovery dramatically, with announcement batches sometimes adding more planets to the catalogue than had been known before Kepler launched. By the end of the first year of science operations, the catalogue of Kepler candidates had grown to over 1,000 potential planets, with dozens already confirmed through detailed analysis and follow-up observation. The numbers themselves told a story, suggesting that planets were far more common than pessimistic estimates had predicted. The galaxy was revealing itself to be a place of remarkable planetary abundance. The discovery of small planets represented one of Kepler's most significant achievements, demonstrating that rocky worlds, comparable in size to Earth, were common throughout the galaxy. Before Kepler, the smallest known exoplanets were several times Earth's mass, and many astronomers wondered whether our planet's size was typical or unusual. The data answered this question decisively, showing that small planets outnumbered large ones significantly. The size distribution of Kepler planets peaked somewhere between Earth and Neptune, in a range where no planet exists in our own solar system. These super-Earths and sub-Neptunes, as they came to be called, represented a common outcome of planet formation that our local examples had not prepared us to expect. Understanding what these intermediate worlds are like, whether rocky or gaseous or something in between, became a major focus of subsequent research. Rocky planets appeared to be ubiquitous, orbiting stars throughout the Kepler field in configurations ranging from Mercury-like scorched worlds to potentially temperate planets receiving about as much radiation from their stars as Earth receives from the Sun. The habitable zone, that region around a star where liquid water could exist on a planetary surface, contained candidates that became priorities for additional study. The abundance of small planets suggested that the processes that form worlds are robust and efficient, producing rocky bodies wherever conditions permit. Our own Earth appeared less special in this context, not a rare cosmic accident, but a common type of world that the galaxy produces in great numbers. This realization carried profound implications for questions about life elsewhere in the universe. Among the thousands of planets Kepler discovered, certain individual worlds captured particular attention because of what they represented, or what they might be like. These planets became famous beyond the astronomical community, their names appearing in news headlines and their properties debated by scientists and public alike. Each memorable discovery added to the emerging picture of planetary diversity that Kepler was revealing. Kepler 22b was announced in December of 2011 as the first planet the mission found orbiting within the habitable zone of a Sun-like star. The planet is roughly 2.5 times the size of Earth, placing it in the category of super-Earths that might be rocky with thick atmospheres or might be more Neptune-like with no solid surface at all. Its orbital period of 290 days places it at a comfortable distance from its star, receiving warmth similar to what Earth receives from our Sun. The discovery of Kepler 22b demonstrated that the mission could achieve its primary goal of finding potentially habitable worlds around stars similar to our own. The planet orbits a G-type star, only slightly cooler than the Sun, located about 600 light-years from Earth in the constellation Cygnus. Whether the planet actually has conditions suitable for life remains unknown, but its discovery proved that such worlds exist and can be found with the transit technique. The announcement generated significant public interest, as it represented a concrete step toward finding another Earth-like world in the universe. Scientists cautioned that the planet's size made it unlikely to be truly Earth-like, more probably a world with a thick gaseous envelope rather than a rocky surface. But the symbolic importance of finding any planet in the habitable zone of a sun-like star resonated widely. Kepler on 6b, announced in September of 2011, captured attention for a different reason, becoming the first confirmed planet found orbiting two stars simultaneously. The planet circles both members of a binary star system, experiencing double sunrises and sunsets that immediately evoked comparisons to Tatooine, the fictional home of Luke Skywalker in the Star Wars films. The discovery proved that circumbinary planets, long staples of science fiction, actually exist in nature. The orbital dynamics of circumbinary planets are complex, requiring the planet to orbit far enough from both stars to avoid gravitational disruption while close enough to remain bound to the system. Kepler 16b occupies such an orbit, circling the stellar pair every 229 days, at a distance roughly equivalent to Venus's orbit around our Sun. The planet itself is a gas giant similar in mass to Saturn, unlikely to harbor life but fascinating as a proof of concept. The Kepler mission would go on to discover several additional circumbinary planets, demonstrating that such configurations are not rare exceptions, but a genuine category of planetary system. The formation of planets in such environments must overcome significant challenges, as the gravitational perturbations from two orbiting stars would seem to inhibit the accretion of material into planetary bodies. Yet nature found a way. These discoveries expanded our conception of where planets could exist, adding binary star systems to the list of environments that produce worlds. Given that roughly half of all Sun-like stars have stellar companions, the habitability of planets around binary stars becomes a question of significant astrobiological interest. Kepler 452b, announced in July of 2015, was described as the most Earth-like planet yet found, though this characterization came with important caveats that scientists were careful to explain. The planet orbits a G-type star, very similar to our Sun, at a distance that gives it a year lasting 385 days. Remarkably close to Earth's own orbital period. Its size, roughly 60% larger than Earth, makes it a candidate for being rocky rather than gaseous. The host star, Kepler 452, is about 6 billion years old, roughly 1.5 billion years older than our Sun, leading some to describe the planet as an older cousin of Earth. If the planet is rocky and has retained an atmosphere, it has experienced conditions within the habitable zone for billions of years, far longer than complex life has existed on Earth. The extended duration of potentially favorable conditions makes the planet intriguing for speculation about biological evolution. The announcement of Kepler 452b generated considerable media attention, with headlines proclaiming the discovery of Earth's twin, or Earth 2.0. Scientists themselves used more cautious language, acknowledging that the planet's composition and atmosphere remained unknown. The larger size compared to Earth means the planet likely has stronger surface gravity and might have a very different geological and atmospheric history. The planet orbits 1,400 light-years from Earth, far too distant for follow-up observations that might characterize its atmosphere or confirm its rocky nature. For now, Kepler 452b remains a tantalizing candidate rather than a confirmed Earth analogue, a world we know exists but cannot yet study in detail. Future telescopes might eventually reveal more about this distant world. The Kepler 11 system, announced in February of 2011, contained 6 planets packed into orbits smaller than that of Venus around our Sun. A configuration unlike anything in our solar system. All 6 planets transit their host star, allowing precise measurements of their sizes, and gravitational interactions between the planets allowed estimates of their masses as well. The system demonstrated that compact multi-planet configurations were common outcomes of planet formation. 5 of the 6 Kepler 11 planets have sizes between those of Earth and Neptune, falling into the super-Earth and sub-Neptune categories that Kepler revealed to be abundant throughout the galaxy. Their densities suggest compositions that include significant amounts of hydrogen and helium gas surrounding rocky or icy cores. The innermost planet orbits in just 10 days, while the outermost of the known planets takes 118 days. The tightly packed nature of the Kepler 11 system raised questions about how such configurations form and remain stable over billions of years. The planets must have migrated inward from their formation locations, as the regions they now occupy would not have contained enough material to build worlds their size. Understanding the migration and settling of planets into stable orbits became a major focus of theoretical work inspired by Kepler discoveries. Systems like Kepler 11 proved to be common rather than exceptional, with many Kepler targets showing multiple transiting planets in compact configurations. The architecture of our own solar system, with well-separated planets and large gaps between worlds, appeared somewhat unusual compared to the tightly packed systems that Kepler frequently found. The diversity of planetary system architectures continued to grow with each new discovery. Kepler 186f, announced in April of 2014, was the first validated Earth-sized planet found in the habitable zone of another star, a milestone that had been anticipated since the mission began. The planet is less than 10% larger than Earth in radius, placing it firmly in the size range where rocky compositions are expected. It orbits a red dwarf star significantly smaller and cooler than our Sun. The orbit of Kepler 186f takes 130 days to complete. But because the host star is so much dimmer than the Sun, this orbit places the planet within the habitable zone where liquid water could potentially exist. Red dwarf stars are the most common type of star in the galaxy, so the discovery of a habitable zone Earth-sized planet around one carried significant implications for the total number of potentially habitable worlds that might exist. The Kepler 186 system contains 5 known planets, all discovered through their transits, with Kepler 186f being the outermost and the only one in the habitable zone. The inner planets orbit too close to the star to maintain liquid water on their surfaces, receiving far more radiation than Earth receives from the Sun. The system demonstrates that red dwarf stars can host complex planetary systems with multiple worlds. The characterization of Kepler 186f remains limited because the host star is relatively faint, making follow-up observations challenging. The planet's mass is unknown, so whether it is truly rocky or might have a significant gaseous envelope cannot be determined with current data. The world remains a tantalizing candidate for habitability, one of the most Earth-like planets known, but still mysterious in its actual properties. The technique Kepler used to find planets is remarkably simple in concept, though demanding in execution. When a planet passes between its star and our line of sight, it blocks a small fraction of the starlight, causing the star to appear slightly dimmer for the duration of the crossing. This dimming is called a transit, and detecting transits is how Kepler found thousands of worlds that could not be seen directly through any telescope. The amount of dimming depends on the relative sizes of the planet and the star, with larger planets blocking more light and producing deeper transits. A planet the size of Jupiter passing in front of a sun-sized star blocks roughly 1% of the light, a dimming easily detectable with modest equipment. An Earth-sized planet crossing the same star blocks only about 84 parts per million of the light, a much subtler signal that requires extraordinary precision to detect reliably. Kepler was built to detect exactly these subtle signals, with instruments sensitive enough to measure brightness changes smaller than 100 parts per million. Achieving this precision required careful attention to every source of noise and variability, from temperature fluctuations in the spacecraft to the intrinsic variability of the stars themselves. The engineering challenges were substantial, but surmountable. The duration of a transit depends on how long the planet takes to cross the visible disk of its star, which in turn depends on the planet's orbital speed and the star's diameter. A planet in a short period orbit crosses the stellar disk quickly, while a planet in a longer orbit moves more slowly and produces a longer transit. For Earth crossing the Sun as seen from a distant star, the transit would last roughly 13 hours. The probability that any given planet will transit its star as seen from a particular direction is not high, as transits require a fortunate alignment where the planet's orbital plane is oriented edge-on to our line of sight. For a planet orbiting at Earth's distance from a Sun-like star, the probability of transit is only about 0.5%. This low probability is why Kepler needed to monitor so many stars simultaneously. By watching over 150,000 stars, Kepler ensured that even with low transit probabilities, a statistically meaningful sample of planets would be detected. If Earth-like planets in Earth-like orbits existed around 10% of Sun-like stars, Kepler should detect several dozen of them, enough to estimate how common such worlds truly are. The large sample size was essential for the mission's scientific goals. The stars Kepler monitored ranged from bright to faint, from small red dwarfs to large yellow stars similar to our Sun. Different types of stars presented different challenges and opportunities for transit detection. Small stars showed larger dimming for a given planet size, making Earth-sized planets easier to detect around red dwarfs than around Sun-like stars. The cadence of observations, with brightness measurements recorded every 30 minutes for most targets, allowed detection of transits lasting from minutes to hours. Some particularly interesting targets were observed at higher cadence, with measurements every minute to capture more detailed information about transit shape and duration. The choice of cadence balanced scientific return against the practical limits of data storage and transmission. Detecting a transit is only the first step in confirming a planet, as other phenomena can produce similar dimming that might be mistaken for a planetary signal. Binary stars where one member periodically eclipses the other produce dimming that can look like a giant planet transit. Background stars that happen to lie along the same line of sight as the target can contribute eclipsing signals that contaminate the measurement. The Kepler team developed sophisticated techniques for distinguishing genuine planetary transits from these imposters, examining the shape and depth of the dimming signal and looking for secondary effects that would reveal the true cause. Planets should produce symmetrical transit shapes, while grazing eclipses of binary stars often show asymmetries. The detailed analysis of each candidate signal was essential for building a reliable catalogue. Ground-based telescopes contributed to the confirmation process by obtaining additional observations that tested whether candidates were genuine planets. Radial velocity measurements could detect the gravitational tug of a planet on its star, providing an independent line of evidence for the planet's existence. High-resolution imaging could reveal background stars that might be causing false positive signals. As the mission progressed, statistical techniques allowed confirmation of planets without individual follow-up. By analyzing the properties of candidates as a population and demonstrating that most were too numerous and too consistent to be false positives. This statistical validation accelerated the confirmation process dramatically, allowing hundreds of planets to be confirmed simultaneously rather than one at a time. The transit method reveals not just the existence of a planet, but also its size through the depth of the dimming signal. A planet that blocks 1% of its star's light has a cross-sectional area that is 1% of the star's visible disk. If the star's size is known from other measurements, the planet's diameter can be calculated straightforwardly. Kepler provided precise size measurements for thousands of planets, building up a picture of the size distribution of worlds throughout the galaxy. The mission showed that planets come in a continuous range of sizes, from smaller than Earth to larger than Jupiter, with no obvious gaps or preferred values. The most common sizes fell in a range between Earth and Neptune, worlds that do not exist in our own solar system. The transit method also reveals the planet's orbital period through the timing of repeated transits. A planet that transits once every 10 days has a 10-day orbital period, while one that transits every 100 days takes that much longer to circle its star. The precision of orbital period measurements improved as more transits were observed over the mission's duration. The shape of the transit light curve, the graph of brightness versus time during the transit event, contains additional information about the planet and its orbit. The sharpness of the brightness change as the planet begins crossing the stellar disk indicates whether the planet crosses near the center or near the edge. The curvature of the bottom of the transit reveals information about the star's brightness variation across its disk. The Kepler spacecraft was designed with a singular focus on detecting planetary transits. Every component optimized for the precise measurement of stellar brightness over extended periods. The telescope carried no other instruments, no backup experiments, nothing that would distract from its primary mission. This focus enabled capabilities that a more general-purpose observatory could not have achieved. The heart of Kepler was a Schmidt telescope design, a configuration that uses both a primary mirror and a corrector lens to achieve a wide field of view with minimal distortion. The primary mirror measured nearly 1.5 meters in diameter, large enough to gather adequate light from the faint stars at the edge of the field of view. The corrector lens at the front of the telescope ensured sharp images across the entire field. The detector at the focal plane of the telescope consisted of 42 charge-coupled devices, or CCDs, arranged in a mosaic that covered the full field of view. These CCDs were similar to the sensors in digital cameras, but far more sensitive and stable. capable of measuring the brightness of stars with the precision needed to detect Earth-sized planets. The total detector contained over 90 million pixels. The CCDs were cooled to -80 to 5 degrees Celsius to minimize electronic noise that would otherwise obscure the subtle signals from planetary transits. The cooling system maintained this temperature steadily throughout the mission, as even small temperature variations would cause changes in detector sensitivity that could masquerade as stellar variability. The spacecraft itself was designed for stability, as any unplanned motion would smear the starlight across multiple pixels and reduce the precision of brightness measurements. 4 reaction wheels, spinning gyroscopes that allow the spacecraft to orient itself without using fuel, kept Kepler pointed at its target field with remarkable steadiness. The pointing accuracy achieved was better than what mission planners had originally required. The orbit Kepler followed was chosen specifically to provide the stable environment needed for continuous observation. Rather than orbiting Earth, where our planet's gravity and magnetic field would cause disturbances, Kepler orbited the Sun in a path that slowly trailed behind Earth. This Earth-trailing orbit provided freedom from the perturbations that would have complicated observations from near-Earth space. The orbit also ensured that the telescope could observe its target field continuously, without Earth blocking the view or the Sun interfering at certain times of year. The target field was positioned so that the Sun never approached too closely as seen from the spacecraft's perspective. This allowed truly continuous observation throughout the mission's duration. Communications with Earth occurred through the Deep Space Network, the collection of large antennas that NASA maintains in California, Spain, and Australia to communicate with spacecraft throughout the solar system. Data accumulated aboard Kepler for approximately 1 month before being transmitted to Earth in concentrated sessions. The science data volume was substantial, reflecting the continuous monitoring of over 150,000 stars. The photometer, the instrument that actually measured stellar brightness, represented the most sophisticated component of the spacecraft. Light from the telescope's optics fell on the detector array, where the arrival of each photon generated electrical charge that could be measured and recorded. The photometer tracked how this charge accumulated over time for each target star. The precision of the photometer allowed Kepler to detect brightness changes as small as 20 parts per million, roughly equivalent to detecting a single firefly against the glare of a car headlight from several kilometers away. This extraordinary sensitivity was achieved through careful engineering of every component in the optical and electronic chain. Calibration of the instrument occurred regularly throughout the mission, as changes in detector sensitivity or optical properties over time could introduce systematic errors into the brightness measurements. By observing stars known to have constant brightness, the team could track and correct for any instrumental changes that developed. The onboard software identified which pixels on the detector corresponded to which target stars, extracting brightness measurements for each star from the raw image data. Only these extracted measurements were transmitted to Earth, as sending the full images for over 150,000 stars every 30 minutes would have exceeded the available communications capacity. The design lifetime of the Kepler spacecraft was 3.5 years, the minimum time needed to detect Earth-sized planets in Earth-like orbits around Sun-like stars. Detecting such a planet requires observing at least 3 transits to confirm the periodic nature of the signal. And for a planet with a 1-year orbital period, This takes at least 3 years. The mission was built with margins that allowed extended operation if the spacecraft remained healthy. In fact, Kepler operated for 4 years in its primary mission configuration, exceeding the design lifetime before mechanical issues intervened. The extended operation allowed detection of planets in longer period orbits and improved the precision of measurements for planets already known. Each additional year of data strengthened the scientific return. The cumulative data from 4 years of observation filled a substantial archive that scientists continue to mine for new discoveries years after the mission ended. Planets that produced subtle signals, detectable only through the combination of multiple transit observations, have continued to emerge from the archived data. The scientific legacy extends far beyond the operational lifetime. The spacecraft was built by Ball Aerospace under contract to NASA, with the photometer developed by NASA's Ames Research Center. The mission represented a collaboration between government, industry, and academic partners that brought together expertise from across the space science community. The success of Kepler reflected the contributions of hundreds of scientists and engineers. The patch of sky that Kepler observed for 4 years lies between 2 easily recognized summer constellations, Cygnus the Swan and Lyra the Harp. On a clear night far from city lights, you can see this region with your own eyes. Though the individual stars Kepler monitored are mostly too faint to see without optical assistance, the telescope's gaze was fixed on this single area for the entire primary mission. The field of view covered roughly 105 square degrees of sky, an area that could be covered by your hand held at arm's length. Within this modest patch, more than 150,000 stars were bright enough for Kepler to monitor with the precision needed to detect transiting planets. The stellar density was high because the field was oriented along our galaxy's disk. The choice of this particular field balanced several considerations that together determined the mission's scientific return. The field needed to contain enough sun-like stars to produce statistically meaningful results about planets around stars similar to our own. It needed to be positioned where continuous observation was possible, without interference from the sun. The field also needed to be located where the stellar density was high enough to fill the detector with interesting targets, but not so high that stars overlapped on the detector and confused the measurements. The Cygnus-Lyra region met these requirements well, providing an optimal balance of target abundance and observational practicality. The stars within Kepler's field ranged from brilliant giants that saturated the detector to faint dwarfs barely above the detection threshold. The primary targets were main sequence stars, those burning hydrogen in their cores as our Sun does, with particular emphasis on G-type and K-type stars similar in temperature and size to the Sun. Red dwarf stars, smaller and cooler than the Sun, made up a significant fraction of the targets and proved particularly fruitful for planet detection. The smaller stellar diameter meant that Earth-sized planets produced larger transits, easier to detect above the noise. Many of Kepler's most interesting discoveries came from these small, cool stars. The distance to stars in the field ranged from relatively nearby, a few hundred light-years, to quite remote, several thousand light-years away. The distance affected how precisely the stars could be characterized, with nearby stars allowing more detailed follow-up observations. Most of the stars were too distant for direct mass measurements, complicating efforts to determine whether detected planets were rocky or gaseous. The stars exhibited a range of ages, from young stellar populations only a few 100 million years old, to ancient stars nearly as old as the galaxy itself. This age diversity meant that Kepler observed planetary systems at different stages of evolution, from newly formed to billions of years mature. The data could potentially reveal how planetary systems change over cosmic time. The field contained stars of varying brightness, and the Kepler team selected which stars would receive the precise monitoring needed for planet detection. Not every star in the field was observed, only those falling on the active detector pixels and meeting selection criteria based on brightness and spectral type. The selection prioritized stars most likely to host detectable planets. Some parts of the detector were used to monitor special targets, including stars known to vary in brightness in scientifically interesting ways. These asteroseismic targets showed oscillations in brightness caused by sound waves propagating through their interiors, vibrations that revealed information about stellar structure and age. The asteroseismic data proved valuable for characterizing the host stars of detected planets. The constancy of the field allowed the accumulation of a dataset unprecedented in its continuity and precision. Other surveys had monitored many stars, but none had watched the same stars so carefully for so long. The 4 years of continuous observation enabled discoveries that shorter campaigns could not have made. After the reaction wheel failures that ended the primary mission, Kepler could no longer maintain stable pointing at the original field and turned to observe other regions of sky in the K2 extended mission. But the original field retained its importance. As the accumulated data continued to yield new planet discoveries through improved analysis techniques, the stars Kepler observed continue shining in that patch of sky tonight, their planets continuing to orbit, regardless of whether any telescope watches for their transits. The worlds revealed by Kepler exist independently of our observation, real places circling distant suns that we happen to catch in the act of crossing their stars' faces. The field that Kepler studied is now the best characterized region of the galaxy in terms of planetary populations. The lessons learned from this one patch of sky extend to the galaxy as a whole, since there is no reason to think this particular region is special in its planetary abundance. The statistics derived from Kepler detections apply to stars throughout the Milky Way, implying that planets are ubiquitous wherever we might look. The single field was a window onto universal truths. Future telescopes have already begun observing stars beyond Kepler's field, and the TESS mission surveys nearly the entire sky for transiting planets around nearby, bright stars. But the depth of understanding achieved for the Kepler field remains unmatched. 4 years of continuous monitoring providing data quality that broader surveys cannot replicate. The original field remains a benchmark. The constellations Cygnus and Lyra will forever be associated with Kepler's discoveries, the region of sky where thousands of worlds were first revealed to human knowledge. On summer evenings, looking toward that part of the sky, we can know that within it lie planets of every type, from scorching hot Jupiters to potentially temperate rocky worlds. The view has meaning now that it lacked before. The earliest discoveries from Kepler came within months of the mission's start, as hot Jupiters and other large planets in short-period orbits produced transit signals that could be detected with relatively little data. These first announced planets established that the mission was working. as designed, and that the galaxy held at least some of the worlds scientists hoped to find. Kepler 4b, announced in January of 2010 alongside 4 other planets from early analysis, was a Neptune-sized world orbiting very close to its host star. The planet completes an orbit in just 3.2 days, placing it so close to its star that the dayside temperature likely exceeds 1,000 degrees. Like many early Kepler discoveries, it was an exotic world unlike anything in our solar system. The first batch of confirmed Kepler planets also included several hot Jupiters, giant planets orbiting their stars in just a few days. These worlds were already known to exist from earlier ground-based discoveries, but Kepler confirmed that they were common enough to appear in the first small sample of data analyzed. The hot Jupiters would prove to be just the tip of a much larger population. The announcements generated excitement, both within the scientific community and among the general public, as tangible results emerged from a mission that had been years in planning and development. The early successes validated the transit method as a powerful tool for planet discovery and demonstrated that Kepler would deliver on its promises. The stream of discoveries accelerated as more data accumulated and analysis techniques improved. Each subsequent data release contained more planets than the last, with the candidate lists growing from hundreds to thousands over the mission's first 2 years. The pace of discovery exceeded what many had anticipated. The February 2011 announcement of over 1,000 planet candidates marked a turning point in exoplanet science, as the sheer number of objects revealed how common planets must be throughout the galaxy. The candidate list contained more potential planets than all previous surveys had detected, and the vast majority would eventually be confirmed as genuine worlds. Among the early candidates were many multi-planet systems, stars showing multiple sets of transit signals from planets at different orbital periods. The Kepler 1.1 system, with its 6 transiting planets announced in early 2011, demonstrated that compact systems with multiple worlds were common outcomes of planet formation. The discovery of multi-planet systems provided opportunities for additional characterization not available for single-planet systems. Gravitational interactions between planets in the same system caused variations in their transit times, allowing mass estimates without the need for ground-based radial velocity observations. This technique became an important tool for characterizing Kepler planets. Small planets began appearing in the candidate lists as enough data accumulated to detect their subtle transits. By late 2011, Earth-sized planet candidates were being reported, though confirming such small signals required extensive analysis to rule out false positives. Each small planet candidate represented a potential milestone. The first confirmed Earth-sized planets were announced in December of 2011, orbiting a star called Kepler 2.0. 2 planets in this system, designated Kepler 2.0e and Kepler 2.0f, had sizes close to that of Earth, though their orbits placed them too close to their star for liquid water to exist on their surfaces. The confirmation proved that Kepler could detect worlds as small as our own. The discovery of Earth-sized planets, even in non-habitable orbits, demonstrated that such worlds were not rare flukes, but part of a continuous distribution of planetary sizes. The mission was detecting exactly the kinds of planets it was designed to find, even if the first examples were too hot to host life as we know it. The scientific papers announcing early Kepler discoveries began filling journals with new information about exoplanet populations, their sizes, their orbital characteristics, and their host star properties. The mission was transforming the field of exoplanet science, even as it continued collecting new data. The pattern of increasing discovery continued throughout the primary mission, with each year bringing more planets and more understanding of planetary populations. The candidate lists grew past 2,000, then 3,000, as new analysis techniques extracted ever fainter signals from the growing data archive. The year 2012 brought the first Kepler planets found in habitable zones, orbiting at distances where surface temperatures might allow liquid water. These discoveries addressed directly the question that had motivated the mission: whether potentially habitable worlds existed around other stars. The answer was clearly yes. By the end of the primary mission in 2013, Kepler had confirmed over 130 planets and identified thousands of additional candidates awaiting confirmation. The pace of discovery had established beyond doubt that planets were common throughout the galaxy, fundamentally changing how scientists thought about the cosmic abundance of worlds. The early discoveries set patterns that would continue throughout the mission and beyond, with each increment of data revealing more planets and refining understanding of planetary populations. The rate of discovery eventually slowed as the easier signals were extracted, but the cumulative count continued growing for years. The confirmed planet count from Kepler grew steadily throughout the mission and continued growing for years after the telescope fell silent, as improved analysis techniques extracted new discoveries from archived data. The catalogue became the most comprehensive inventory of exoplanets ever assembled, revealing patterns and populations that transformed understanding of planetary systems. The growth came in pulses as the Kepler team periodically released new candidate lists based on accumulated observations. Each release generated excitement and intensive follow-up work, as scientists around the world examined the new candidates and sought to confirm them as genuine planets. The community effort accelerated the pace of validation. Statistical validation techniques allowed mass confirmation of planets without individual radial velocity observations, by demonstrating that the population of candidates was too consistent and too numerous to be dominated by false positives. A validation study in 2014 confirmed over 700 planets simultaneously, more than doubling the confirmed count in a single announcement. The validation approach relied on careful analysis of the signals and the stars producing them, assessing the probability that each candidate was genuine based on its characteristics. Candidates that passed stringent tests were promoted to confirmed status, while ambiguous cases remained candidates pending additional information. The approach was conservative, accepting small losses to avoid false confirmations. By 2016, the confirmed count from Kepler had passed 1,000, a milestone that underscored the mission's remarkable productivity. Many of these planets were smaller than Neptune, a category that had been virtually unknown before Kepler, and that proved to be the most common type of planet in the galaxy. The 1,000-planet milestone represented far more than a round number, demonstrating that planet formation was an efficient process that produced worlds around most stars. The statistical analyses that accompanied the confirmations estimated that rocky planets in the habitable zones of Sun-like stars might number in the billions throughout the Milky Way alone. The catalogue continued growing after the primary mission ended, as scientists continued analyzing the 4 years of data collected during Kepler's prime operations. Planets in longer period orbits, which produced fewer transits during the observation window, gradually emerged from the noise as more sophisticated techniques were applied. The final Kepler mission data release, incorporating all observations from both the primary and K2 missions, enabled discoveries that continued for years. Planets that had been just below the detection threshold became accessible as analysis improved, adding incrementally to the catalogue. The candidate list remained larger than the confirmed list throughout the mission, as full validation of every candidate was not practical given the resources required. Many candidates have high probabilities of being genuine planets, but have not been formally confirmed through the rigorous processes required for that designation. The distinction between confirmed and candidate planets matters for some scientific purposes, but less for others. Statistical studies of planetary populations can use the entire candidate list with appropriate corrections for false positive rates, while claims about individual planets require higher confidence. Both levels of certainty contribute to understanding. By the time the telescope was retired in 2018, Kepler had confirmed over 2,700 planets, with thousands of additional candidates still awaiting validation. The numbers far exceeded what anyone had anticipated when the mission was proposed, demonstrating that the galaxy was even richer in planets than optimistic predictions had suggested. The continuing analysis of Kepler data means that the final count of confirmed planets from the mission remains uncertain, with new confirmations still emerging years after operations ended. The data archive continues yielding discoveries as techniques improve and computing power increases. The growth of the catalogue revealed patterns in planetary populations that could not have been discerned from smaller samples. The size distribution showed clear features, with a gap between super-Earths and sub-Neptunes that suggests a physical boundary between rocky and gaseous planets. The period distribution showed how planet formation favors certain orbital configurations. Multi-planet systems showed correlations in the sizes and spacings of sibling worlds, suggesting that planet formation within a single disk produces families of similar planets. Systems with one small planet tended to have other small planets, while systems hosting large planets showed different characteristics. The architecture of planetary systems varied widely, from tightly packed configurations with multiple worlds inside Mercury's orbit, to more widely spaced arrangements more reminiscent of our solar system. The diversity demonstrated that planet formation can produce many different outcomes depending on initial conditions and subsequent evolution. Statistical studies using the full catalogue enabled estimates of how many potentially habitable planets the galaxy might contain. The numbers were encouraging, suggesting billions of rocky planets in habitable zones throughout the Milky Way. Kepler could not study these worlds in detail, but it proved they exist in abundance. Beyond the individual planets it discovered, Kepler taught us fundamental lessons about planetary systems throughout the galaxy. Lessons that could only be learned through the statistical analysis of thousands of detections. The mission revealed how common planets are, what sizes they come in, and how they arrange themselves around their host stars. The most basic lesson was that planets are not rare but ubiquitous, with essentially every star hosting at least one world on average. This finding transformed the cosmic context for questions about life elsewhere in the universe. If planets are everywhere, then the opportunities for life to emerge are similarly widespread. Before Kepler, Pessimistic estimates suggested that planets might form around only a fraction of stars, that our solar system might be unusual in possessing multiple worlds. The data refuted these concerns decisively, showing that planet formation is a robust process that operates wherever stars form from clouds of gas and dust. The abundance of planets means that the Milky Way contains hundreds of billions of worlds, more than the number of stars. Some stars host one planet, some host several, and the total count exceeds what even optimistic predictions had anticipated. The galaxy is crowded with worlds. The size distribution of planets revealed by Kepler showed that small planets are more common than large ones, a pattern that has significant implications for understanding planet formation. Jupiter-sized planets exist, but they are relatively rare compared to the super-Earths and sub-Neptunes that dominate the planetary population. The most common planet size in the Kepler catalogue falls between Earth and Neptune, a category with no representative in our own solar system. These intermediate worlds might be rocky planets with thick atmospheres, or they might be ice giants with deep gaseous envelopes, or something else entirely. Understanding their nature remains an active area of research. The size distribution shows a gap, or valley, between about 1.5 and 2 Earth radii, suggesting a physical transition between rocky planets and those with substantial gaseous envelopes. Planets just below the gap appear to have lost any initial atmospheres, while those just above have retained their gas. The gap reveals something fundamental about how planets evolve. Rocky planets similar in size to Earth prove to be common, removing any concern that our planet's size might be a cosmic fluke that would not be replicated elsewhere. The galaxy contains billions of rocky worlds, some fraction of which orbit at distances where surface temperatures might permit liquid water. The orbital periods of Kepler planets showed that close-in orbits are heavily populated, with many planets circling their stars in days or weeks, rather than months or years. These short-period planets would have been too hot to form where they now orbit, implying that migration moved them inward from more distant birthplaces. Planets on longer-period orbits, taking months or years to circle their stars, were detected but in smaller numbers because the transit method is less efficient at finding them. A planet in a year-long orbit produces only a few transits during a 4-year mission, making detection more difficult than for planets that transit dozens of times. The habitable zones of Sun-like stars, where orbital periods range from roughly half a year to several years, contain planets that Kepler could detect but not characterize in large numbers. The mission confirmed that such planets exist, even if the sample remains smaller than for close-in worlds. The population of long-period planets remains less well characterized than that of short-period planets, a gap that future missions will work to address. Understanding the full range of orbital configurations requires complementary techniques and longer observation campaigns. The architecture of planetary systems showed remarkable diversity, from single planets to systems with half a dozen or more worlds detected through transits. The multi-planet systems revealed through Kepler demonstrated that complex arrangements are common outcomes of planet formation. Many Kepler systems showed a distinctive pattern of compact, tightly packed planets, with several worlds orbiting closer to their star than Mercury orbits our Sun. These systems have no analogue in our solar system and required revision of theories about how planets space themselves during formation and migration. The coplanarity of multi-planet systems The tendency for planets to orbit in nearly the same plane was confirmed by the high incidence of multiple transiting planets around single stars. If planetary orbits were randomly oriented, multiple transits would be rare, but the high multiplicity rate showed that flat, disk-like planetary systems are common. Orbital resonances, where the periods of different planets form simple ratios like 2:1 or 3:2, appeared frequently in Kepler multi-planet systems. These resonances suggest that planets migrated through their protoplanetary disks and became captured into stable configurations as they moved. The host stars of Kepler planets spanned a wide range of types, from small red dwarfs to large yellow stars like our Sun. Planets proved common around all stellar types, though the characteristics of planetary systems showed some dependence on the properties of their host stars. Metal-rich stars, those containing higher abundances of elements heavier than helium, appeared more likely to host giant planets than metal-poor stars. This correlation had been suggested by earlier ground-based surveys and was confirmed by Kepler's large sample. The metals in a star's composition reflect the material available for building planets. Smaller planets showed less dependence on stellar metallicity, suggesting that the formation of rocky worlds is less sensitive to the heavy element content of the protoplanetary disk. This finding has implications for the frequency of potentially habitable planets around different types of stars. Binary star systems, where two stars orbit each other, proved capable of hosting planets despite the gravitational complications that such configurations introduce. Both circumbinary planets, orbiting both stars, and planets orbiting just one member of a binary pair, were found, demonstrating the robustness of planet formation. In May of 2013, the Kepler mission faced a crisis that threatened to end its observations permanently. When the second of the telescope's 4 reaction wheels failed, and the spacecraft could no longer point precisely at its target field, the moment marked the end of the primary mission as originally planned. Reaction wheels are spinning devices that allow spacecraft to orient themselves without expending fuel. By transferring angular momentum between the wheels and the spacecraft body, Kepler carried 4 reaction wheels, though only 3 were needed to maintain stable pointing in all 3 axes. One wheel had failed previously in 2012. When the second wheel failed, the spacecraft was left with only 2 functioning wheels, insufficient to counteract the forces that pushed it off target. The pressure of sunlight on the spacecraft's surfaces, though extremely gentle, was enough to rotate the telescope away from its targets over time. Without 3 working wheels, this rotation could not be controlled. The immediate response was to place the spacecraft in a safe mode that protected its systems while engineers assessed the situation and considered options. The telescope stopped collecting science data and oriented itself in a low-power configuration that did not require precise pointing. Engineers attempted to restore one of the failed wheels to operation, hoping that the damage might not be permanent or that some functionality could be recovered. These efforts continued for months, with various diagnostic tests and recovery procedures tried. The recovery attempts ultimately failed, confirming that both failed wheels had suffered permanent damage that could not be repaired remotely. The Kepler spacecraft, as originally designed, could not continue its mission of staring at a single field with the precision required to detect Earth-sized planetary transits. The announcement of the primary mission's end came in August of 2013, after all recovery options had been exhausted. 4 years and 4 months after launch, Kepler could no longer do what it had been built to do. The news was disappointing, but not unexpected, given the months of failed recovery efforts. The failure did not diminish what Kepler had already accomplished during its years of successful operation. The data collected during the primary mission contained information about thousands of planets, much of which had not yet been fully analyzed. The legacy was secure regardless of what happened next. The engineering team refused to give up on the spacecraft entirely, seeking creative solutions that might extract additional science from the crippled observatory. With only 2 reaction wheels, precise pointing in all 3 axes was impossible, but perhaps something useful could still be done. The key insight was that the pressure of sunlight, which had been the problem for maintaining stable pointing, could also be part of the solution. By orienting the spacecraft so that sunlight pressure balanced equally on both sides, a kind of equilibrium could be achieved that required only 2 reaction wheels to maintain. This balance could only be maintained for fields of view along the plane of the spacecraft's orbit around the Sun, where the solar pressure was symmetric. The technique would not allow observation of the original Kepler field, but could permit observation of different fields along a belt around the sky. A K2 mission concept emerged from these engineering studies, proposing that Kepler be reborn as a survey telescope that would observe different patches of sky in campaigns lasting approximately 80 days each. The spacecraft would not match its former precision, but it could still detect transiting planets. NASA approved the K2 mission in May of 2014, and observations began shortly thereafter, with the spacecraft operating in its new configuration. The technique of balancing solar pressure proved workable, allowing scientifically useful measurements despite the degraded pointing capability. The first K2 observations focused on testing the new operating mode and characterizing its performance. The precision achieved was lower than during the primary mission, but still sufficient to detect planets larger than Earth around relatively bright stars. The reborn telescope could contribute new discoveries. K2 could not match the 4 years of continuous staring that had made the primary mission so powerful for detecting small planets in long-period orbits. But the ability to observe different regions of sky opened new scientific opportunities, including planets around stars too bright for the original field. The K2 mission continued until October of 2018, when the spacecraft finally exhausted its fuel supply and could no longer point its antenna toward Earth to transmit data. The second act had lasted 4.5 years, nearly as long as the primary mission. During that time, K2 observed 19 different fields of view across the sky, each revealing new worlds and new stellar phenomena. The extended mission proved that creative engineering could extract remarkable science from a damaged spacecraft. The story of the reaction wheel failure and recovery illustrates how space missions often succeed despite setbacks that might seem insurmountable at first encounter. The engineers who designed Kepler could not have predicted exactly how the spacecraft would fail, but they had built-in redundancy that nearly saved the mission entirely. When that redundancy proved insufficient, the same engineering creativity that designed the telescope found a way to continue operating in a modified form. The spacecraft that seemed finished in 2013 continued making discoveries for another 5 years. The psychological impact on the mission team was significant, as years of work had gone into planning observations that could now never be completed as intended. The original mission had been designed to observe the same stars continuously for at least 3.5 years, building up the repeated transits needed to confirm planets in long-period orbits. Losing that capability meant losing the chance to find the most Earth-like planets, those in year-long orbits around Sun-like stars. The team had to adjust their expectations while searching for new possibilities. The 4 months between the wheel failure and the official end of the primary mission were filled with uncertainty and intense effort to find solutions. Engineers worked around the clock testing recovery procedures, while scientists calculated what could be accomplished with various degraded configurations. The atmosphere was one of determined problem-solving rather than despair, with everyone focused on what might still be possible. The eventual K2 solution emerged from this crucible of creativity. The announcement of the K2 mission was greeted with relief and renewed optimism by the scientific community that had invested so much in Kepler's success. The telescope would continue contributing to exoplanet science, even if in a different form than originally planned. The new observing strategy opened possibilities that the original fixed-field approach had not allowed. Sometimes limitations create opportunities that would not otherwise have been recognized. The technical details of how K2 achieved its balancing act reveal the ingenuity required to operate a crippled spacecraft for years beyond its expected lifetime. The 2 remaining reaction wheels controlled the spacecraft's orientation around 2 axes, while the solar pressure and careful positioning controlled the 3rd. The balance point was unstable, requiring constant small corrections that consumed more fuel than the original mission would have used. This is ultimately why K2 ended when the fuel ran out, rather than continuing indefinitely. The fields of view available to K2 were constrained to regions along the ecliptic plane, the path the Sun appears to follow through the sky over the course of a year. This constraint arose from the need to keep the sunlight pressure balanced symmetrically on the spacecraft, which was only possible for certain orientations. Fortunately, the ecliptic plane crosses many interesting regions of the sky, including star clusters, nearby stars, and areas previously unexplored for transiting planets. The constraints proved less limiting than initially feared. Each K2 observing campaign lasted approximately 80 days, the time between when a particular field became observable and when it passed too close to the Sun to continue viewing safely. This shorter baseline, compared to the 4 years of the primary mission, meant that planets with longer orbital periods were harder to detect and confirm. K2 was most sensitive to planets in short-period orbits, hot worlds that completed their years in days or weeks rather than months. The trade-off was accepted as necessary. The data processing for K2 observations required new techniques to correct for the less stable pointing, as the spacecraft drifted more than during the primary mission. Scientists developed sophisticated algorithms to remove the effects of spacecraft motion from the brightness measurements, recovering much of the precision that the mechanical problems had degraded. These techniques improved throughout the K2 mission as experience accumulated and methods were refined. The final K2 data products approached the quality of the original mission, despite the hardware limitations. The transition from Kepler to K2 demonstrated that scientific missions are not simply about hardware, but about the people who operate the hardware and analyze the data it returns. The same team that had designed and operated the primary mission adapted to the new circumstances and made K2 a success. Their expertise with the spacecraft and its instruments proved invaluable for extracting the maximum science from the damaged observatory. The human element was as important as the engineering solution. The K2 mission also benefited from being unexpected, as the scientific community had prepared for Kepler to end in 2013 and was pleasantly surprised by the extended observations. Proposals flooded in from researchers wanting to observe targets that K2 could access, more proposals than the available time could accommodate. The oversubscription demonstrated the ongoing hunger for exoplanet data and the value that even degraded observations could provide. K2 had become a highly competitive facility. The legacy of the reaction wheel failure extends beyond K2 to future mission designs, which now incorporate lessons learned from Kepler's experience. Reaction wheels remain common components of spacecraft, but engineers consider their failure modes more carefully when planning missions. The creative response to Kepler's problems has inspired thinking about how other missions might be adapted if similar failures occur. The experience enriched the collective knowledge of the spaceflight community. The failure also highlighted the importance of archiving data properly, as the observations Kepler collected before the wheel failure continued yielding discoveries for years afterward. Scientists returned to the archived data repeatedly, finding new planets that earlier analyses had missed and refining the properties of planets already known. The data became a resource that outlasted the spacecraft's active operations. The investment in careful data preservation paid dividends. The emotional journey of the Kepler team through the failure and recovery deserves recognition as part of the mission's story, alongside the technical achievements and scientific discoveries. The disappointment of losing the primary mission was real and deeply felt by people who had devoted years of their careers to making it succeed. The satisfaction of finding a path forward with K2 was equally real, a validation of persistence and creativity. The human experience of the mission included both setbacks and triumphs. The public followed the drama of the reaction wheel failure with interest, as Kepler had become one of the most prominent NASA missions of its era. News coverage explained the problem and the attempts to solve it, bringing general audiences into the story of spacecraft engineering. When K2 was announced, the response was broadly positive, with appreciation for the ingenuity that had saved the telescope. The mission had become a narrative that people cared about. The reaction wheel failure was not the only challenge Kepler faced during its operational lifetime, though it was the most dramatic and consequential. Earlier problems with detector anomalies and data transmission issues had been resolved without fundamentally changing the mission. The spacecraft had proven resilient to various smaller setbacks before the wheel failure posed an existential threat. This history of problem-solving prepared the team for the biggest challenge. The K2 mission that emerged from the failure became scientifically valuable in its own right, discovering hundreds of planets and contributing to many other areas of astronomy beyond exoplanet science. The ability to observe different fields opened K2 to stellar astrophysics, supernova observations, and studies of solar system objects that pass through its field of view. The reborn telescope became more versatile than its original incarnation had been. Limitation had transformed into opportunity. The K2 mission began formal science operations in May of 2014, after months of testing the new observing technique that balanced the spacecraft against solar radiation pressure. The reborn telescope embarked on a series of observing campaigns that would, eventually, cover 19 different fields of view, across the sky. Each campaign lasted approximately 80 days, targeting a new region before the geometry changed and a different field became accessible. The cadence created a rhythm of discovery that continued for more than 4 years. The first K2 campaign focused on a field in the direction of the constellation Pisces, testing whether the new operating mode could produce scientifically useful data despite the degraded pointing precision. The results exceeded expectations, demonstrating that planets could indeed be detected and that the data quality, while lower than the primary mission, was sufficient for meaningful discoveries. The proof of concept opened the way for the subsequent campaigns that would follow. K2 was ready to contribute. The scientific priorities for K2 evolved throughout the mission, as the community learned what the reborn telescope could accomplish and what limitations remained unavoidable. Early campaigns emphasized nearby bright stars, where the larger transit signals and easier follow-up observations could produce well-characterized planets despite the reduced precision. Later campaigns expanded to include star clusters, where many stars at the same distance and age could be observed simultaneously. The flexibility of observing different fields became a scientific asset. One of K2's most significant contributions was the discovery of planets around stars, much closer and brighter than those in the original Kepler field, making them excellent targets for detailed follow-up observation. The original Kepler field had been chosen for its abundance of sun-like stars at moderate distances, but these stars were relatively faint, limiting what follow-up telescopes could learn about the planets orbiting them. K2's brighter targets enabled mass measurements through radial velocity observations and atmospheric characterization through transit spectroscopy. The proximity that K2 could access proved scientifically valuable. The K2-18 system, discovered during Campaign 1, became one of the most important K2 discoveries when atmospheric observations by the James Webb Space Telescope revealed intriguing chemistry in the planet's atmosphere. K2-18b is a sub-Neptune world orbiting in the habitable zone of its red dwarf star, receiving similar amounts of radiation to what Earth receives from the Sun. The tentative detection of molecules associated with biological activity on Earth has made this planet one of the most discussed in exoplanet science. The discovery demonstrates how K2's focus on nearby systems created opportunities that the original mission could not have provided. The TRAPPIST-1 system, though discovered by ground-based telescopes, was observed extensively by K2 during Campaign 12, providing critical data for characterizing the 7 Earth-sized planets orbiting that dim red dwarf star. The K2 observations refined the orbital periods and sizes of the planets, contributing to the detailed portrait of this remarkable system. The collaboration between K2 and ground-based facilities illustrated how different observatories work together to maximize scientific return. K2's contribution to TRAPPIST-1 understanding demonstrated the value of the extended mission. Multi-planet systems were a specialty of K2, which discovered numerous stars hosting 2, 3, or even more transiting worlds detectable in the 80-day observing windows. These compact systems, with multiple planets packed into tight orbits, provided insights into planetary formation and the gravitational interactions that shape planetary architectures. The transit timing variations caused by gravitational perturbations between planets allowed mass measurements without radial velocity observations. K2 revealed the complexity of planetary systems throughout the solar neighborhood. Young stars and star clusters received particular attention during K2 campaigns, as these environments could reveal planets at different stages of evolution than the mature systems Kepler primarily observed. The Hyades and Pleiades clusters were observed, along with younger stellar associations where planets might still be contracting and cooling from their formation. Observing planets around young stars provides windows into how worlds evolve over billions of years. K2 opened this temporal dimension of planetary science. The Prasepe cluster, also known as the Beehive, yielded several planetary discoveries that showed how planetary occurrence rates might vary with stellar age and environment. Comparing planets in clusters to those around isolated field stars tests whether the formation environment affects the final planetary populations. K2's ability to observe clusters that happen to fall within accessible fields made these comparisons possible. The original Kepler field contained few cluster members. Beyond exoplanets, K2 contributed to many other areas of astronomy that benefited from its continuous, precise photometry of large numbers of stars. Asteroseismology, the study of stellar oscillations that reveal internal structure, produced results for thousands of K2 targets. Eclipsing binary stars were characterized in detail, providing precise measurements of stellar masses and radii. Stellar rotation periods were measured for vast numbers of stars, contributing to understanding of stellar spin-down over time. The telescope served multiple communities. Supernovae, observed in real time by K2, provided unprecedented views of these stellar explosions from the earliest moments of brightening. Because K2 was watching continuously, it caught several supernovae while they were still rising to maximum brightness, capturing data that ground-based surveys typically miss. The early light curves constrained theoretical models of what triggers these explosions and how the blast wave expands through the stellar envelope. K2's continuous coverage proved valuable for transient phenomena. Solar system objects that crossed the K2 field of view were observed serendipitously, including asteroids, comets, and distant trans-Neptunian objects. The precise photometry allowed rotation periods to be measured and surface features to be inferred from brightness variations. These observations came essentially for free, byproducts of the exoplanet search that required no additional observing time. K2 became an accidental solar system observatory. The supermassive black holes at the centers of distant galaxies, known as active galactic nuclei, were monitored by K2 to study their variability patterns on timescales of hours to weeks. The continuous coverage revealed fluctuations that ground-based monitoring could not capture due to day-night cycles and weather interruptions. These observations contributed to understanding the accretion processes that power the brightest objects in the universe. K2's reach extended far beyond exoplanets. The community that utilized K2 data extended well beyond the original Kepler team, as the open data policy made observations available to researchers worldwide shortly after collection. Scientists who had never worked on Kepler before contributed discoveries and analyses based on K2 data. The democratization of access expanded the scientific return far beyond what any single team could have achieved. The policy set a precedent for subsequent missions. Guest observer programs allowed scientists to propose specific targets for K2 observation, competing for time through a peer review process similar to other major observatories. This competitive allocation ensured that the limited observing time went to the highest priority science, as judged by the scientific community rather than the mission team alone. The diversity of approved programs reflected the breadth of science K2 could address. The telescope served many masters. The analysis techniques developed for K2 data pushed the boundaries of what could be extracted from imperfect observations, as the reduced pointing stability required innovative approaches to data processing. Software tools created for K2 analysis became standard resources that benefited other missions and ground-based surveys as well. The challenge of working with K2's quirks drove advances in the field. Limitations spurred innovation. Citizen scientists contributed to K2 through projects like Planet Hunters, which invited volunteers to examine light curves and identify transit signals that automated algorithms might miss. Thousands of participants examined K2 data, discovering several confirmed planets through visual inspection. The involvement of non-professional scientists expanded both the workforce analyzing data and public engagement with the mission. K2 became a community enterprise. The geographic diversity of K2 targets meant that follow-up observations could be coordinated with telescopes in both hemispheres, as different campaigns covered different parts of the sky. Southern Hemisphere observatories could access some K2 fields that northern facilities could not, and vice versa, enabling worldwide participation in characterizing discoveries. The original Kepler field was accessible only from the northern hemisphere, limiting follow-up options. K2 engaged a global network. The cumulative impact of K2 continued growing long after the mission ended, as archived data yielded new discoveries through reanalysis with improved techniques. Planets that were missed in initial searches were found in subsequent passes through the data, with better algorithms. The archive will remain scientifically productive for decades, just as the original Kepler archive has continued producing results years after the primary mission ended. The investment in data preservation ensures ongoing return. The contrast between K2 and the original Kepler mission illustrates how different observing strategies reveal different populations of planets and serve different scientific goals. Kepler's long stare at a single field enabled detection of planets with orbital periods up to years, including Earth-sized worlds in Earth-like orbits. K2's sequential campaigns could not match this capability, but instead surveyed a much larger fraction of the sky, albeit with shorter observation windows. Each approach had strengths. The K2 mission officially ended on October 30th, 2018, when the spacecraft ran out of the fuel needed to maintain its orientation and communicate with Earth. The final commands placed Kepler in a safe configuration that does not interfere with other spacecraft, and the telescope now orbits the Sun silently, as a testament to what it accomplished. The extended mission had added 4.5 years of operations beyond the primary mission failure. K2 had exceeded all expectations. On October 30th, 2018, NASA announced that the Kepler Space Telescope had exhausted its fuel and could no longer maintain the orientation needed to transmit data back to Earth. The announcement marked the formal end of a mission that had transformed our understanding of planets throughout the galaxy. After 9.5 years in space, the telescope that had discovered thousands of worlds finally fell silent. The end came not suddenly, but gradually, as fuel levels declined over the final months of operations. The final weeks of the mission were managed carefully, with engineers stretching the remaining fuel as far as possible. while still completing valuable observations. The last K2 campaign concluded successfully, with data transmitted to Earth before the spacecraft's ability to point its antenna became unreliable. The end was orderly rather than catastrophic, a graceful conclusion to a remarkably productive mission. Kepler had earned its rest. The final commands sent to Kepler configured the spacecraft into a safe mode that ensures it will not interfere with other missions or create hazards in its orbital environment. The telescope now trails behind Earth in its orbit around the Sun, gradually drifting farther from our planet as the years pass. The spacecraft will continue orbiting for millions of years, a silent monument to human curiosity and ingenuity. The hardware endures even though the mission has ended. The legacy of Kepler extends far beyond the spacecraft itself, living on in the data archives that scientists continue mining for new discoveries years after the last observations were collected. The archives contain brightness measurements for hundreds of thousands of stars, a treasure trove that will remain valuable for decades. Researchers regularly announce new planets found in archived Kepler data, using improved techniques to detect signals that earlier analyses missed. The data is a gift that keeps giving. The planetary catalogue that Kepler created remains the foundation of exoplanet statistics, the primary source for understanding how common different types of planets are throughout the galaxy. When scientists estimate that there are more planets than stars in the Milky Way, they base that estimate largely on Kepler's discoveries. The statistical framework derived from Kepler's systematic survey informs essentially all discussions of planetary prevalence. No other mission has contributed comparable statistical power. The TESS mission, launched in 2018 shortly before Kepler's retirement, carries forward the search for transiting planets with a different strategy that complements rather than replaces what Kepler accomplished. TESS surveys nearly the entire sky rather than staring at a single field, finding planets around bright nearby stars that are ideal for detailed follow-up observation. The missions form a continuum, with Kepler providing the statistical foundation and TESS identifying the best individual targets for characterization. The baton was passed smoothly. The James Webb Space Telescope, which began science operations in 2022, observes atmospheres of planets that Kepler and its successors discovered, searching for the molecular signatures that might indicate habitable conditions or even life. Without Kepler's discoveries, Webb would have few suitable targets for these groundbreaking atmospheric studies. The connection between planet discovery and planet characterization creates a chain of investigation that spans multiple missions and decades. Kepler's discoveries feed the science of the future. Future missions currently in development, including the European Space Agency's Plato and NASA's Nancy Grace Roman Space Telescope, build on lessons learned from Kepler's operations and science. Plato will search for transiting planets with a design informed by Kepler's experience, while Roman will use gravitational microlensing to survey planetary populations that Kepler's transit method could not access. The family of planet-hunting missions continues growing. Kepler was the pioneer. The scientific papers published using Kepler data number in the thousands, with more appearing regularly as researchers continue analyzing the archived observations. The mission has generated one of the largest literature bodies in modern astronomy, reflecting the breadth of science enabled by Kepler's unique capabilities. These papers range from individual planet discoveries to broad statistical analyses, to stellar astrophysics enabled by the continuous, precise photometry. The intellectual legacy is vast. The impact on public understanding of the cosmos may be Kepler's most important legacy, as the mission brought the reality of exoplanets into general awareness in a way that previous discoveries had not accomplished. Before Kepler, exoplanets were a specialized topic known mainly to astronomers and science enthusiasts. After Kepler, the existence of planets around other stars became common knowledge, part of the general understanding of what the universe contains. The mission changed how humanity sees its place in the cosmos. The announcement of individual Kepler discoveries regularly generated worldwide news coverage, with planets like Kepler 452b making headlines as potential Earth cousins orbiting distant stars. These stories reached audiences far beyond the scientific community, inspiring wonder about what other worlds might be like and whether life might exist on any of them. The cultural impact of Kepler extended well beyond its technical achievements. The mission mattered to people who would never read a scientific paper. Educational programs incorporated Kepler's discoveries into curricula at all levels, from elementary school lessons about planets to graduate courses in astrophysics and planetary science. The mission provided teaching examples that made abstract concepts concrete, showing students what science could reveal about distant worlds. Young people who were children during Kepler's operations may pursue careers inspired by its discoveries. The educational legacy extends across generations. The citizen science programs associated with Kepler, particularly Planet Hunters, engaged hundreds of thousands of volunteers in examining real data and contributing to actual discoveries. This participation gave non-scientists a direct role in the scientific process, demonstrating that meaningful contributions could come from anyone with curiosity and patience. Several confirmed planets were discovered first by citizen scientists before professional astronomers noticed them. The mission expanded. Who could participate in science? The technological innovations developed for Kepler influenced subsequent spacecraft designs as engineers applied lessons learned about photometer precision, data handling, and long-duration operations to new missions. The experience of operating Kepler through the reaction wheel failure and K2 recovery provided valuable knowledge about spacecraft resilience and creative problem-solving. These lessons became part of the institutional knowledge that NASA applies to future projects. The engineering legacy parallels the scientific one. The international collaboration that Kepler fostered brought together researchers from dozens of countries working together on data analysis, follow-up observations, and theoretical interpretation of the discoveries. The mission demonstrated that planetary science operates as a global enterprise, with expertise distributed worldwide and results benefiting everyone. The networks of collaboration built during Kepler's operations continue facilitating research on subsequent missions. Scientific relationships outlast any single project. The economic impact of Kepler, though difficult to quantify precisely, includes the training of scientists and engineers who contributed to the mission, and the technological spin-offs that found applications beyond astronomy. The precision photometry techniques developed for Kepler have influenced other fields that require extremely accurate measurements of light intensity. The investment in the mission produced returns that extended beyond its primary scientific purpose. Space missions generate broad value. The philosophical implications of Kepler's discoveries prompted renewed discussion of humanity's place in the universe and the possibility of life beyond Earth. Knowing that billions of planets exist in our galaxy alone, many of them potentially habitable, changes how thoughtful people consider questions about cosmic significance and the likelihood that we are alone. The mission provided data that informs ancient questions. Science and philosophy intersected. The end of Kepler was acknowledged with appropriate ceremony, as NASA held press events and published commemorative materials recognizing what the mission had accomplished. Team members who had worked on the project for decades reflected publicly on their experiences, sharing both the challenges and the triumphs of the long campaign. The celebration was tinged with sadness at the ending, but dominated by pride in the achievement. The mission deserved commemoration. The spacecraft itself continues orbiting the Sun, slowly drifting farther from Earth, carrying the memories of thousands of worlds its instruments detected during the years it watched the sky. The telescope cannot see anymore, but what it saw remains preserved in data archives, accessible to anyone who wishes to explore them. The physical hardware and the digital legacy travel different paths into the future. Both endure. The team members who built, launched, and operated Kepler have moved on to other projects, carrying their experience to new missions and new challenges. Some work on tests or upcoming planet hunting missions, applying lessons learned from Kepler's success. Others have moved to different areas of space science or retired from active research. The human network dispersed but remains connected. The mission created lasting professional bonds. The story of Kepler continues being told in documentaries, books, and educational materials that introduce new audiences to what the mission accomplished and how it changed our understanding of the cosmos. Each retelling reaches people who were not following space science during the mission's operations, expanding the legacy with each year. The narrative has become part of science history. Kepler's story endures. The galaxy revealed by Kepler contains more planets than stars, billions upon billions of worlds, orbiting suns that span the full range of stellar types and ages. This fundamental insight, derived from one telescope staring at one patch of sky for a few years, transformed our understanding of how common planetary systems are throughout the cosmos. Before Kepler, we hoped that planets were numerous, but could not prove it with data. After Kepler, the abundance of worlds became established fact. The statistics Kepler provided allow estimates of planetary populations that extend far beyond the stars the telescope actually observed, because the sample was large enough and systematic enough to support extrapolation. Scientists can now calculate how many Earth-sized planets likely exist in the habitable zones of Sun-like stars throughout the Milky Way, arriving at numbers in the billions. These calculations would have been impossible before Kepler demonstrated how common such worlds actually are. The implications are staggering. The diversity of planets Kepler revealed exceeded what our single solar system had suggested was possible, with worlds ranging from giant scorching hot Jupiters to small rocky planets cooler than Earth. Planets orbit in days or in years, alone or in packed systems, around stars ranging from red dwarfs far smaller than the Sun to yellow giants nearing the end of their lives. The zoo of known exoplanets defies simple categorization, each world presenting its own combination of properties. The cosmos is more creative than our imaginations. The super-Earths and sub-Neptunes that dominate Kepler's catalogue have no counterparts in our solar system, representing a class of planets we had not anticipated before discovering them around other stars. These worlds, larger than Earth but smaller than Neptune, may be the most common type of planet in the galaxy. Yet we know little about what they are actually like. Are they rocky worlds with thick atmospheres, or water worlds with deep global oceans, or something else entirely? Kepler posed questions that remain unanswered. The planets in multi-planet systems often orbit closer together than the spacing in our solar system would suggest is possible, packed into tight configurations that seem crowded by our standards. These compact systems challenge theoretical models of planetary formation and evolution, suggesting that migration and orbital rearrangement play important roles in shaping planetary architectures. The orderly spacing of our solar system may be unusual rather than typical. Kepler revealed our parochial assumptions. The habitable zone planets Kepler discovered represent perhaps the most tantalizing portion of its legacy. Worlds receiving stellar energy comparable to what Earth receives from the Sun, and therefore potentially capable of supporting liquid water on their surfaces. Dozens of such planets are now known, orbiting stars throughout the galactic neighborhood, each one a possible location for life to have emerged. We cannot yet determine whether any of these worlds are truly habitable, but their existence changes how we think about life's prospects. The candidates are real. Kepler 442b orbits a star somewhat cooler than the Sun, receiving about 2/3 as much energy as Earth, but still potentially warm enough for liquid water if a suitable atmosphere provides greenhouse warming. Kepler 186f was the first Earth-sized planet found in a habitable zone, a milestone that demonstrated Kepler could detect the worlds it was designed to find. Kepler 452b orbits a Sun-like star in an orbit remarkably similar to Earth's, though the planet itself is larger than our world. Each discovery added another entry to the list of places to investigate. The question of life on these distant worlds cannot be answered by Kepler's data alone. But the mission identified targets that subsequent observations might someday characterize well enough to search for biosignatures. The James Webb Space Telescope has begun this work, analyzing atmospheres of select Kepler-discovered planets for the molecular fingerprints that might indicate biological activity. The chain from discovery to characterization to potential biosignature detection stretches across decades and multiple missions. Kepler was the first link. The philosophical weight of Kepler's discoveries falls differently on different minds, but the basic fact of planetary abundance seems to carry implications that few can ignore entirely. The universe contains more worlds than any human could count in a lifetime, more destinations than any civilization could explore in 1 billion years, more possibilities than any imagination could exhaust. This plenitude, demonstrated rather than merely speculated, changes the texture of human thought. We are not alone in the sense that we once feared. The night sky that stretches above you now, wherever you happen to be listening, contains the stars that Kepler observed and countless others that no transit survey has yet examined. Each of those stars likely hosts at least one planet. Many of them host several, and some fraction of those planets reside in regions where conditions might permit liquid water and perhaps life. The canvas is not empty, but crowded with worlds, most of them invisible to any current technology, but present nonetheless. The darkness is full. The constellation Cygnus, where Kepler stared for 4 years, contains the specific stars whose planets fill the catalogue of confirmed discoveries. On a clear night from the northern hemisphere, you can look toward that constellation and know that somewhere in that direction, thousands of planets orbit stars too faint to see with unaided eyes. The abstraction of planetary statistics becomes almost tangible when connected to a specific direction in the actual sky. Kepler looked there, and there it found worlds without number. The Lyra region adjacent to Cygnus also fell within Kepler's field of view, including the bright star Vega that ancient astronomers knew and named millennia before anyone suspected planets might exist around it. The blending of ancient observation and modern discovery creates a continuity across human history, connecting the sky watchers of the past to the planet hunters of the present. We look at the same stars they looked at, but we see more. Kepler expanded what seeing means. The future holds discoveries that will build on Kepler's foundation, revealing planets in greater detail, discovering worlds in regions Kepler could not observe, eventually perhaps finding evidence of life beyond Earth. Each step forward will incorporate what Kepler taught, the statistical context and the individual examples that the mission provided. Scientists not yet born will cite Kepler data in papers not yet conceived, extending the legacy indefinitely. The mission's influence stretches into futures we cannot imagine. The patience that Kepler demonstrated, staring at the same stars for years without looking away, mirrors the patience that scientific inquiry requires when addressing the deepest questions. The search for other worlds and for life beyond Earth cannot be rushed, cannot be forced to yield answers on human schedules, cannot be completed by any single mission or any single generation. Kepler contributed what it could during its operational lifetime, and the work continues through other efforts. Progress is gradual. The telescope that now orbits the Sun silently, its instruments cold and its mission complete, represents what dedicated human effort can accomplish when focused on a question worth answering. The engineers who designed it, the scientists who analyzed its data, the administrators who funded and managed it, and the public who supported the enterprise through their interest and their taxes, all contributed to what Kepler achieved. The mission was a collective undertaking, and its success belongs to everyone. The data Kepler collected will remain accessible for decades, a resource that future researchers will mine for discoveries we cannot anticipate with current understanding. The archive grows more valuable as analytical techniques improve, revealing planets and phenomena that were hidden in the noise when the data was first collected. Scientists will return to Kepler's observations again and again, extracting new knowledge each time. The investment pays compound interest. The quiet of the night accompanies these thoughts of distant worlds, the stillness of late hours matching the stillness of the space through which Kepler drifts. The telescope made its contribution and now rests, its work done, its legacy secure. The galaxies continue their slow rotations, the stars continue their nuclear burning, and the planets continue their patient orbits, regardless of whether any observer watches. The cosmos proceeds as it has for billions of years. The sleep that approaches, if it approaches, comes in a universe far richer than anyone knew before Kepler launched. A cosmos filled with worlds that orbit every star and await only the instruments sensitive enough to detect them. The knowledge of this abundance can be carried into rest, a background awareness that the night sky contains more than it appears to contain, that the darkness hides wonders. Kepler revealed this truth. The specific discoveries fade into the general understanding, the individual planet names becoming less important than the overall insight that planets are everywhere. Kepler 22b and Kepler 452b and Kepler 1865 join the thousands of other entries in a catalogue too large to remember in detail. What matters is the cumulative weight, the statistical certainty that the galaxy teems with worlds. The forest matters more than any individual tree. The stars outside your window, if you can see them, or the stars hidden by clouds or city lights, or the daylight of a different time zone, continue shining as they have for billions of years. Some of them host planets that Kepler discovered. Most of them host planets that remain unknown. And all of them are part of a galactic community that includes our own solar system. We belong to this community of stars and worlds. Kepler showed us our neighborhood. The mission is complete, but the story continues, written in the data archives and the scientific papers, and the public understanding that planets exist around every star. The next chapter belongs to Tess and Webb, and missions not yet launched. The search goes on, and the discoveries accumulate, and the picture of planetary abundance sharpens with each passing year. Progress does not stop. Kepler rests now, its work done, its legacy secure in the thousands of worlds it revealed and the billions more it proved must exist. The telescope that changed our understanding of the cosmos orbits the sun in silence, trailing behind Earth on a path that will carry it through the centuries and millennia ahead. The hardware endures, even as the mission ends. The worlds Kepler found remain in their orbits, circling their stars in the same rhythms they followed, long before any telescope watched for their shadows. The planets do not know they were discovered, do not care that instruments measured the dimming their transits caused. They simply exist, as they have for millions or billions of years, as they will continue to exist for ages to come. The night continues wherever you are, and the stars that Kepler observed continue shining 40 years of travel time away at the speed of light. The knowledge the telescope provided accompanies humanity from this point forward, a permanent addition to what our species knows about the universe we inhabit. We are richer for what Kepler taught us. Rest now with the knowledge that the galaxy is full of worlds. The planets orbit every star in the night sky, that the cosmos contains more destinations than any voyage could exhaust. Kepler revealed this abundance, and the revelation stands regardless of what future missions discover. The foundation is laid, the telescope sleeps, and you may sleep too, knowing that the search continues and that the universe waits with patience for however long understanding takes to grow. The worlds are out there, the stars shine on, and the story of discovery extends into futures we cannot see. Good night from the drowsy astronaut. Sleep well, and we'll explore the cosmos together again soon.